In this video, we will study together the Unigram language model subword tokenization algorithm. The overall training strategy of a Unigram language model tokenizer is to start with a very large vocabulary and then to remove tokens at each iteration until we reach the desired size. At each iteration, we will calculate the loss on our training corpus thanks to the Unigram model. As the loss calculation depends on the available vocabulary, we can use it to choose how to reduce the vocabulary. So we look at the evolution of the loss by removing in turn each token from the vocabulary. We will choose to remove the p%, which increases the loss the less. Before going further in the explanation of the training algorithm, I need to explain what is a Unigram model. The Unigram language model is a type of statistical language model. A statistical language model will assign a probability to a text considering that the text is in fact a sequence of tokens. The simplest sequence of tokens to imagine are the words that compose the sentence or the characters. The particularity of Unigram language model is that it assumes that the occurrence of each word is independent of its previous word. This assumption allows us to write that the probability of a text is equal to the product of the probabilities of the tokens that compose it. It should be noted here that it is a very simple model which will not be adapted to the generation of text, since this model will always generate the same token, the one which has the greatest probability. Nevertheless, to do tokenization, this model is very useful to us because it can be used to estimate the relative likelihood of different phrases. We are now ready to return to our explanation of the training algorithm. Let's say that we have a training corpus with 10 times the word hug, 12 times the word bug, 5 times the word lug, 4 times bug, and 5 times dog. As said earlier, the training starts with a big vocabulary. Obviously, as we are using a toy corpus, this vocabulary will not be that big, but it should show you the principle. The first method is to list all the possible strict substrings, and that's what we will do here. We could also have used the BPO algorithm with a very large vocabulary size, but for now, the strict substrings are enough. The training of the Unigram tokenizer is based on the expectation maximization method. At each iteration, we estimate the probabilities of the tokens of the vocabulary, and then we remove the p% of tokens that minimize the loss on the corpus and which do not belong to the basic character, as we want to keep in our final vocabulary this basic character to be able to tokenize any word. Let's go for it. The probability of a token is simply estimated by the number of operands of this token in our training corpus, divided by the total number of operands of all the tokens. We could use this vocabulary to tokenize our words according to the Unigram model. We will do it together to understand two things: how to tokenize a word with the Unigram model, and how the loss is calculated on our corpus. The Unigram LM tokenization of a text, hug, will be the one with the highest probability of occurrence according to our Unigram model. To find it, the simplest way to proceed will be to list all the possible segmentation of our text, hug, calculate the probability of each of these segmentation, and then choose the one with the highest probability. With the current vocabulary, two tokenizations get exactly the same probability, so we choose one of them and keep in memory the associated probability. To compute the loss on our training corpus, we need to tokenize, as we just did, all the remaining words in the corpus. The loss is then the sum over all the words in the corpus of the frequency of the occurrence of the word multiplied by the opposite of the log of the probability associated with the tokenization of the word. We obtain here a loss of 170. Remember, our initial goal was to reduce the vocabulary. To do this, we will remove a token from the vocabulary and calculate the associated loss. Let's remove, for example, the token hug. We notice that the tokenization for hug with the letter H on the tuple hug is now impossible. Nevertheless, as we saw earlier that two tokenizations had the same probability, we can still choose the remaining tokenization with a probability of 1.10 minus 2. The tokenization of the other words of the vocabulary also remain unchanged. And finally, even if we removed the token hug from our vocabulary, the loss remained equal to 170. For this first iteration, if we continue the calculation, we will notice that we could remove any token without it impacting the loss. We will therefore choose at random to remove the token hug before starting a second iteration. So we estimate again the probability of each token before calculating the impact of each token on the loss. For example, if we remove now the token composed of the letter H and U, there is only one possible tokenization left for hug. The tokenization of the other words of the vocabulary is not changed. In the end, we obtain by removing the token composed of the letter H and U from the vocabulary a loss of 168. Finally, to choose which token to remove, we will, for each remaining tokens of the vocabulary, which is not an elementary token, calculate the associated loss. Then, we will compare this loss with them. The token which we will remove is the token which impacts the least the loss. Here is the token B. We had mentioned at the beginning of the video that at each iteration we could remove 10% of the token per iteration. The second token that we could remove at this iteration is the token D. And that's it. We just have to repeat these steps until we get the vocabulary of the desired size. One last thing. In practice, when we tokenize a word with a unigram model, we don't compute the set of probabilities of all the possible splits of a word before comparing them to keep the best one. But we use the Viterbi algorithm, which is a really much more efficient way to do it. And that's it. I hope that this example has allowed you to better understand the unigram tokenization algorithm.